And then lately, in 48-volt node DC to DC, whether it be for automotive or for very high-density computing, we've had an awful lot of uptake, and I would say that we're pretty much GaN is sweeping, and I'll explain why. So, to give you a background, at EPC, we're in a 5th generation of GaN. So, over the last 10 years, 9 years of production, we've gone through 5 generations. 5th generation is shown here in the dark green line. I'll keep showing you this. But there are 5 main areas where GaN has a clear advantage over MOSFETs. And I'm going to go through those advantages right now. One is die size. And on the vertical axis, you have die size for a given voltage. Right? So these are different voltages. So you can see, for example, at 100 volts, this dotted blue line is the theoretical limit for silicon. And it's 4x smaller than the theoretical limit. Okay, so there's a big advantage to GaN because it's smaller. Okay? By the way, this dot is 300x away from the theoretical limit for GaN. This is the theoretical limit for silicon. So there's a long way to go. But advantage to GaN, 4x smaller. Okay? Let's go. There we go. Next one, switching speed. Switching speed comes from 2 main components. One is capacitance, and the other one's inductance. I'll first deal with the capacitance. This is a gauge of basically how much charge you have to pump into a device to change its state from on to off. So you can look at it as the vertical axis is switching speed, the horizontal axis is voltage. Once again, theoretical limit for silicon, right there. That's actually the Johnson limit. And there you can see we're 5x better than the theoretical limit for silicon. So theoretically, on the capacitance spectrum, we can be 5 times faster getting the charge in to change the state. But that's only half the story, because the other half is inductance, and that's another advantage for GaN, especially if you buy our GaN, because how many of you know that I hate packages? I hate packages of all kinds, all the time. I spent a lifetime packaging semiconductors, and it's nothing but trouble. Not only that, it never adds to the performance of the device. Think about that for a minute. Packages only detract. And here's one of the big ones. So, these are popular packages, okay? DirectFET, by the way, big international rectifier package while I was there, is the best package in the world in terms of inductance and also thermal resistance. But so this, and look at 1 megahertz, what fraction of the switching losses comes from the package inductance. Or even with the very best packaged device for a silicon device, 50-50. In other words, it doubles your switching losses because of package inductance. Now, if you get one of our little guys, no package. Why? Because I hate packages. But also, you only get 18% losses. And those come from actually the inductance of the PC board traces. So, we have 3 advantages so far. Die size, capacitance, inductance. Okay, let's keep going. Next one. I get a lot of questions about this. They say, oh, those tiny little guys, don't you have a problem thermally? And the answer is, well, you always have a problem thermally, but it's better than anything else. So this is a cartoon showing our device flipped up, upside down, mounted onto a PC board. So these are PC board traces. These are the little bars, solder bars that you saw. And these are various layers in the PC board. Again, it's a cartoon. This is your junction, where your junction temperature is. And when you're worried about the thermal management of your device, you got to look at all the ways that heat gets out. And you do that in terms of thermal resistances. So one is down into the PC board. We call that theta JB. There it goes. Up to the back surface, theta JC. You look at a bunch of silicon parts that give you theta JCs all day long. Okay? And then you've got to the ambient from your board, and then you've got to the ambient from the case. But you also have, in the case of a packageless device, sidewall radiation. The sidewalls on all but our largest devices are actually more area than the top surface. So it more than doubles, like origami thing, folds out, and it's more than double the effective area of the device as a result. So you get a thermal advantage, and we can quantify that. So this is showing you the thermal resistance junction to case. area here, comparing against, once again, the direct FET, most thermally efficient package. The red dots are silicon, and then you can see about a 6x advantage in terms of getting the heat out through the device. If you look at heat into the PC board, that's limited by the PC board resistance. So you have a thermal advantage, you have an inductance advantage, capacitance advantage, and you have a die size advantage, right? Said there were more than that, right? So here is the one that most people just don't realize, and that is that our 5th generation parts are all priced right in the middle of MOSFETs in high volume. These are, in each case, in each grouping, we took the 10 most popular parts in Asia at volume. And we priced our new Generation 5 right in the middle of it. So I won't say it's an advantage, but it's neutral. The advantage comes on the next slide. When you get rid of a package, you get better reliability. This is just showing you a spectrum of all of our parts that we have around today. But we have 100 billion hours we've tracked in the field now, and we have a total of 5 device failures. Now, I used to build 1 billion MOSFETs every 6 weeks. And for 10 years, I only had field problems from the package. It's the package that causes reliability problems. There are thermomechanical interfaces, dissimilar materials, all sorts of bad stuff going on in there, wire bonds that are welded to your part, and everything's moving around all the time with moisture getting in and out. Our parts are glass passivated, and they got none of that nonsense. And therefore, there's really not much to fail. All right, so where are we going with this? Okay, again, is at the early days. I told you 300x away from theoretical. So here's where we are, and there's your theoretical limit again. When I started in MOSFETs, which was before almost everybody here was born, we started 1978, introduced our first MOSFETs, and lo and behold, they were 300x away from the theoretical limit calculated by Lidow. And that's this line right here. So now we're 300x away from there, and hey, it took me about 20 years to get here. It's going to take about 20 years to get there, but we'll get there. So we're just at the early days. But here's the short-term roadmap in more tangible terms. That's our Generation 4 devices. We came out with Generation 5 devices a little over a year ago. That's what it looks like. It's about half the size of the Gen 4. And we're right now working on Gen 6, then Gen 7, and Gen 8. And then we're starting to get into limitations of how to get the current out of the bumps themselves. So this becomes a very different problem. You know, in digital logic, you have the problem of how do you make your line width smaller because then your transistors are smaller and you squeeze more in there. Well, with us, our problem is that as you get smaller, your current density is going up, but you don't have more room to get your current out. So you got to start doing things to minimize that. And one of them is make ICs. And an example of that is our first phase, which was about 4 years ago, when we married 2 devices onto one chip in the form of a half bridge, a monolithic half bridge. So think about, for those of you who know, 80% of all power conversion applications use some form of a half bridge. And they all, if you look at a half bridge, it's got 2 transitions, one on top of the other. It's got a drain and a source and a drain and a source. Okay, well, if you make a monolithic half bridge, you have a plus, a ground, a switch node. I just saved 30% of my bumps. That is a big deal when you're bump limited. Okay, so step 1, gotta get these power devices together. Can't do that in silicon, not above a certain really low voltage, like 10, 12 volts. So this is big. The step 2 is every one of our GaN devices has a driver in front of it. So let's stick the driver on there too. So step 2, we introduced these parts a year ago, where you glue the driver onto the same, well, it's on the same chip, it's in GaN, with the FET. And here's 2 of them. These were made for wireless power for Class E amplifiers. We're great, 7 megahertz, saves a ton of money, because look at how little that area is compared to this is the device it's driving right here, there's 2 of them. It's just a tiny little area, like less than a square millimeter. So what's phase 3? And phase 3, you can go over our booth and see phase 3. We're just showing for the very first time here at APEC, and that's actually taking the whole half bridge which everybody in power conversion does this 80% of the time. You've got power devices, you've got drivers, you've got a level shift, you've got other kind of crap like a sync boot. Always, over and over and over again. You can buy a silicon IC, you can buy transistors, glue them together, design your PC board, or you can get this device, which we're showing for the very first time here at our booth. There's a fully monolithic power stage. And I would contend that this is where power conversion is going for the future. This redefines what a component is. Discrete power transistors are only discrete power transistors because we couldn't figure out how to integrate them in silicon. We tried, and we tried, and we tried, and so nowadays you can in GaN, because GaN integrates very easily multiple power devices. This is showing you running at 10 amps, about 95% efficient at a megahertz. This is the closest silicon series, several points lower. So this is where the future is really going to go. And our intention is to take this, add more features and functions, make full closed loop systems, three-phase, full bridges, synchronous rectifiers, and that whole spectrum of devices that as design engineers we spend our lives making out of discrete transistors. All right, so in conclusion, between 60 and 400 volt devices, GaN has a clear advantage, and chip scale has a clear advantage. Chip scale beyond 400 volts is not practical because your terminal separation is bigger than the chip, so you're going to need to put a package. Maybe you can get away with 500 volts, but probably not. So for all those folks making 600 volt devices, they got a package wrapped around their thing, and it's because they need it. But below that, you don't need it, so don't do it, because it only makes 6 volts. The advantages of size, switching speed, thermal, cost. By the way, when I was making a billion MOSFETs every 6 weeks, at the end of the month I'd get a bill for packaging and I'd get a bill for silicon, and they were the same. Packages cost as much as the chip inside on average. And as you go to smaller chips, the package costs more. So by getting rid of the package, you get rid of half the cost. That's pretty cool too. And of course, reliability. You get rid of all those reliability problems. The other thing is GaN can be integrated. So we're not only at the early stages of GaN technology, we're at 300x greater power density than we can achieve, but we are also just at the beginning of integration. Where now we have a monolithic power stage, and then that's really a starting point for system on a chip kinds of integration. And as I mentioned, we're 300x away. So just to draw a conclusion to this, silicon's dead. Anybody want to argue that point? Look, you can push as much current as you want. It just depends on how big you make your chip. I don't remember what our 350 volt chips close current rating is, but I do remember that our 300 volt, our 30 volt chip has a close current rating of 590 amps, and it's 12 square millimeters. It's just a whole lot of current that you can run through it. And our LiDAR customers use that stuff. LiDAR runs right up against our pulse current limits.
What about continuous current?
So continuous current it depends on, continuous current depends on a lot of things. Our devices tend to be continuous current limited by the electromigration limits of the metal layers. So the current is set based on how much current you can get to a ball. Now we're right now upgrading, and you'll see it at our booth. We're going to a half generation step where we're replacing these balls with copper bars and an additional thick copper layer so we can get more DC current out of it.
So like I was mentioning before your presentation, right now IR 215 volts, 45 amps is about what you can get for space radiation.
Yeah.
Can I put 45, can I get that?
Oh yeah, no, we have.
On your half bridge?
On the half bridge, we don't have a 200 volt half bridge.
Okay.
So, but on our discretes, yeah, you can get better than that. Yeah, the EPC 2034, it's like 30 amps, something like that. Anyway.
Okay. on an E. And I keep talking to you about curving.
Yeah.
And security is on and how do you get the E on.
Yeah, and so when you look at DC current, sometimes that's just a specsmanship thing. But in our case, most of it's limited by electromigration.
We're all integrated on the PCB, right?
Pardon me?
We're integrated on the PCB. What temperature do you limit when you're built on the board?
So the question is, what temperature do we limit when we're on the board? And most PCB manufacturers will limit it to 105, some go up to 120. So our devices are all rated at 150. And it's hard to use 150 because of the thermal resistance to the board. But there are people like in space that put them on ceramic. By the way, we run our device at 400 degrees C, not recommended. But GaN's limitations are primarily from solder. Solder limits. All right, well, there are no questions. I've exhausted your questions here.
Is that right?
And I want everybody to go out there and stop buying silicon. Yeah. Except for digital. You can do that. It's okay.
Is that right? I can vaguely remember you have to limit the max operating voltage to 80% of the rated breakdown for maximum plant load.
So the question is, do you have to limit the maximum operating voltage to 80% of the limit? And the answer is no. The answer is no. You can run them up to the limit. A lot of people do that for conservatism. And that's just conservatism, but you don't have to. All right, well, I'll hang around if there are any other questions.